Hello. The topic today, which we are going to discuss, is from A levels physics, and the name of the topic is gravitational fields. The learning objective of our today's topic are gravitational field and gravitational force between point masses. So first, we are going to talk about the gravitational field, that what is gravitational field, and then we are going to discuss about the gravitational force that exists between the point masses or the masses. So first, starting with our previous topic, previously we have covered the mass and weight, and we have discussed that mass is basically the amount of the matter present in any body or any object, whereas the weight is the gravitational pull on any mass or any object by the earth. For example, as you can see in this picture, there is a mass of some object placed on the surface of the earth, and because of this mass there must be some gravitational force acting on this object in downward direction. So there's a downward force which is known as weight, or the gravitational force which is acting on this object due to the mass of this earth and the mass of this object itself. And it is given by the formula W equals to mg, where W is representing the weight of the object, M is representing the mass of the object, and G is basically representing the gravitational field strength. So in today's topic, we are going to talk about this gravitational field strength and how does this gravitational field strength changes as we move our mass away from the surface of Earth, or if we take two masses of some two objects of some masses, how the gravitational field can change between these two masses. Now the question arises is that does this formula apply if we move something far away from this earth, which means that the formula which we have just learned, W equals to mg, will we use the same formula if we move this mass away from the surface of the earth? Let us suppose if I pick this mass and I place it at some height from the earth. Okay, so this is the height which I have taken this object from the surface of the earth. Now this object is not placed on the surface. It is at certain height from the center of the earth. So can we apply the same formula to calculate the gravitational force? The answer is no. And the reason is that as we move our object away from the surface of the earth, the gravitational field strength of the earth changes, which means that the gravitational field is not as strong as it was near to the surface of the earth. So if we are moving away from the surface of the earth, the gravitational field will become weaker and weaker, and because of that the gravitational force and the weight of the object will also become less. The force of the gravity is carried by the field lines and non-contact force. As with all forces, it is vector and its direction point towards anything with mass. So as we know that force is basically a vector quantity. So if it is a vector quantity, so it must be represented by the arrow. So similarly, the field lines, the lines which are representing the gravitational field, are always represented by a line and arrow like this. So if I draw the lines which are representing the gravitational field, so these lines will be known as the gravitational field lines or gravitational force lines. Now, what is a gravitational field? The gravitational field is any region in the space where any mass is going to experience the force. So let us suppose if we put some mass near to the surface of the earth, so that object or that mass is going to experience the gravitational pull of the earth. Now, the reason why it is feeling that gravitational pull of the earth is because of the gravitational field which is around the surface of the earth. Similarly, all the masses have some of the gravitational field around them due to their masses, and we can represent these gravitational field by making the lines which are known as gravitational field lines or force lines. As you can see in this diagram, in the first diagram, you can see there are several lines drawn side by side, and all of these lines are basically representing the gravitational field. So if you see the first diagram is labeled as A, whereas the second diagram is labeled as B. Now, what's the difference between these two diagrams is that in the first diagram, the lines are very close to each other, whereas in the second diagram, the lines are not as close to each other, but they are far away from each other. So what does it represent? These lines are representing that the field is constant, it's uniform. Why? Because if you see the distance between the lines for the first case, you can see that the distance between the consecutive two lines are the same wherever I measure. If I measure from the bottom, the distance is the same. If I measure from the middle, the distance is same. If I measure from the top, the distance between two lines are the same. Similarly, if you look at the diagram B, you can see that the distance in the between the two lines is also same. So if the distance between two field line is same, so we say that the field is constant or the field is uniform. So these two diagrams, A and B, are representing a constant or a uniform gravitational field. But what is the difference? As you can see in the first diagram, the lines are closer to each other. So we will say that the field is stronger for the first diagram. So the field for the first diagram, part A, is uniform and constant, but it has more field strength. The gravitational field strength of the first diagram is more, whereas the gravitational field strength for the second diagram is less. As you can see that the value of G for the first diagram is 16 Newton per kilogram, whereas the diagram number B, the gravitational field strength is 8 Newton per kilogram. So what does this mean? This means that in the first diagram, the object which is kept near to the surface will experience a force of 16 Newton per kilogram, which means that per kilogram or per unit mass of the object is going to experience a force of 16 Newton. Whereas for the second one, if I keep an object near to the field of the second one, it is going to experience a force of only 8 newtons per kilogram, which means that every 1 kilogram of the mass or every per unit of the mass is going to experience a force of 8 Newton. So I can say that the field strength of the first diagram is stronger and the field strength of the second diagram is weaker. Now coming to the next diagram, which are below, there are three diagrams which are drawn below. So if you look at the first one, I can name it as 1. This can be named as 2, and this can be named as 3. So in diagram number 1, again, the distance between the lines is constant. So if the distance between lines are constant, so this means that it's a uniform or a constant gravitational field. So the first diagram is representing a uniform or a the constant gravitational field, and the arrowhead is showing you the direction of the field, that the field is pointing towards the right side. The second diagram is also the diagram for the gravitational field, and it is also showing you the direction towards the right side. But what's the difference? This field is not uniform. Why it's not uniform? Because if you look at the distance, at the start it was less, and the end the distance was more. So as the lines are moving forward, they are spreading out. So if they are spreading out, so this means that the distance between them is increasing. So that means that the field strength is decreasing. Similarly, if you look at the diagram number 3, this the field line was spread out in the start, but at the end of the diagram, you can see that they are coming close to each other. So as they are closing each other, so this means that the field is increasing because there are more lines close to each other. So if there are more lines close to each other, each line is representing that there's a gravitational field here. There is some type of gravitational force felt here. So if there are more lines close to each other, we say that the field is stronger. And if there are less lines close to each other, or you can say if the lines are spread out, we say that the field is decreasing. Now, as you can see that first, if we look at diagram number 1, the diagram number 1 is a diagram which we see in our daily life, a man standing on a surface, and you will see that the field for every person standing on the surface of the earth is approximately constant. So there will be a uniform gravitational field if we take a small area. But if we are looking our earth from a far distance, for example, if we are sitting on a planet which is far away from the earth, so we are going to see this second view of the earth, as you can see in the diagram number 2. So what you are going to experience here, you are going to see that the gravitational field lines are coming towards the earth's surface like this. And in this case, you are going to see that the field lines are spreading out when they are going far away, and they are coming closer to each other when they are near to each other. So we can say that in this case, the field is not uniform. And this field around the earth is known as radial. This is a radial gravitational field around the surface of the earth. And when we look at a larger scale, we are going to find that the field around the earth is not uniform. But when we look at a smaller scale, for example, in this classroom, if you look at in the classroom, and if we were able to see the gravitational field, we will view it as a uniform field. The closer together the field lines, the larger the gravitational field strength. The reason the gravitational force decrease as you go away from the planet because the field lines become more spread out. So as we are moving away from the surface of the earth, for example, if someone is sitting here and he go to this position and then he go to another position and then he go to far more position from this earth. So as you can see that the lines in between this person has spread out. So if the lines are spreading out, so this means that the gravitational field is decreasing as we are going far away from the earth. But as we are coming towards the surface of the earth, the field lines are closing up. So if the field lines are closing up, we will say that the gravitational field is increasing as we are coming towards the surface of the earth, and it is decreasing as we are going away from the surface of the earth. Now we have another diagram just to understand. Let us suppose we have two masses. So here these dots are representing two masses. So let us suppose this is mass number 1 and this is mass number 2. So we have some questions about these masses. So first of all, you can see that there are field lines which are represented, which are moving towards these masses, which is indicating that the gravitational field is towards these masses, which means that the force is going to pull any object which will be placed near to these masses towards this object. So there will be a force of attraction. So the first question says that which of the two masses is heavier? So the heavier mass must have greater gravitational force, and the greater gravitational force means that there must be a greater gravitational field strength, and the greater gravitational field strength is represented by close gravitational field lines. So if you look at the diagram, in the first diagram you can see that the distance between the lines is small, whereas for the second diagram, the distance between two lines is bigger. So we can easily say that for the diagram number one, for the mass number one, the mass number one is more massive. It is heavier because the field lines are close to each other, and it will have greater gravitational force around it and greater gravitational field around it. And the mass number two will have smaller gravitational field around it. That is why it is having this the field lines which are far away from each other. The second question says that draw the arrow show the direction of the field of at each of the point A and B. Now you can see the point A and B shown on the picture. So if we have to show the direction of the electric field line on this point A, we are going to make a arrow like this indicating the direction of the field like this. Number 3, at which point A or B the field is stronger? So of course at A the field will be stronger. Why? Because the field lines are closer to each other at point A. Whereas if we look point B, the field lines are far away from the point B. So that is why when the field lines are closer, we say that the field strength is more. And when the field lines are far away from each other, we say that the field strength is less. Mark any X at a point where the object could sit and not feel any force. So we have to see a point where there is no gravitational field acting. So I can mark this point X here, and I can say that this point X is a point where there is no gravitational field. Why? Because this point is between the two masses, and because of these two masses, the field line between this point will be cancelled out by these two masses. So this is a point where if any object sits, it is not going to experience any gravitational field, because the gravitational field on either side of this point is the same. So if both the masses are pulling the person sitting at point X at the same magnitude, so it's just like that there is no field acting at this point. Free fall for the gravitational field. So as we have discussed that the gravitational field strength or the gravitational field is the area in which the gravitational force is felt, and gravitational field strength is basically the force acting per unit mass. So the force acting per unit mass can be measured by the unit Newton per kilogram. So this is the unit for field strength. Whereas if we look a unit for the acceleration of a free falling object, let us suppose this is the surface of the earth, and there is an object, a ball, which is falling towards the surface of the earth. So it will be accelerating towards the surface at a gravitational acceleration g, that is 9.8. 1 Newton per kilogram. So the gravitational acceleration and the field strength both have the same units. And similarly for the gravitational acceleration, because it's the acceleration, we can also use a unit meter per second square. So this means that both of these quantities, the gravitational field strength and the gravitational acceleration, can be represented by a same symbol, that is g, and it has a same value, that is 9.81, and we can use a same unit for them as well, that is Newton per kilogram. So they mean the same, although they can be described in a different way. Now, talking about the Newton's law of gravitation. So, as we were talking about two masses which are placed at a distance from each other, so of course they are not going to experience a force equal to W equals to mg or F equals to mg, because there's a distance between them. They are not sitting on the surface of the earth. So, how we can calculate the force for such two masses which are at a distance from each other? For example, here this is mass number 1 and this is mass number 2. I can label it M1 and I can label it M2. And they are at a distance of R. So R is basically representing a distance between between these two masses. Now, these two masses are basically, let's suppose, in a sphere. And we are assuming that this sphere is a uniform sphere having a uniform mass inside itself. And if we are assuming that this sphere is having a uniform mass, so we can also assume that the mass of the sphere must be lying in the center of the sphere here. So what we have to do, that whenever we measure the distance between two objects, we can consider them as a point masses, which means that we consider that the mass of these objects are lying in the center. So that is why when we measure the distance, we will always measure the distance between two objects from their centers, not from their outer surface. So as you can see that we measure the distance between them from their center position, and we represent them as R, and the masses are represented by M1 and M2. So if we want to find a force between them, that will be attractive force between them. It will not be a repulsive force, because the gravitational force is always attractive. So we can find by creating a formula. And we know that the force between these two masses will be proportional to the product of their masses, M1 and M2, which means that if I take the product of these two masses, then that product will be directly proportional to the force between them, which means that more the product of their masses, more will be the force between them. Less the product of their masses, less will be the force between them. And similarly, the law says that the force is inversely proportional to the square of the distance between them. And it means that the force and the distance are inversely proportional to each other. Inversely proportional means that if we are increasing the distance between two objects, the force must decrease. And similarly, if we are decreasing the distance between two objects, between the center of two objects, then the force must increase. So this is showing an inverse relationship. But it's not just an inverse relationship, it is square of the distance. Okay, so if I combine these two expression, expression number 1 and expression number 2, or equation number 1 and equation number 2, I can write it in this form. F directly proportional M1 M2 over R square. And I can call it expression number 3 or equation number 3. Now, as you can see that there's a sign of proportionality in them. Now, we have learned that whenever we finish the sign of proportionality, we have to introduce a equality and a constant between them. So I can also write it as F equals to G M1 M2 over R square. So here G is basically the gravitational constant which I have introduced in the equation to remove the sign of proportionality. And this G is basically a constant. And you know that constant is basically something whose value is not changing. So this G, the capital G, is known as gravitational constant, and its value is given by 6.67 into 10 raised power to minus 11. So from here, we get the formula to measure the force between two masses Okay, as you can see that there's a mass m1 and m2 here in the picture, and they are separated by a distance r, so they must be exerting the force on each other. And this force which they are exerting on each other can be find out by using this formula G m1 m2 over r square, where m is the mass of the first object, m2 can be the mass of second object, whereas r is basically representing the distance between them, the distance between the center of these two objects. And g is basically a gravitational constant which is represented by 6.67 into 10 to the power 2 minus 11, and the value of g will never change, it will always remain the same. So we can consider one example and we can see that what is the gravitational force between them. So let us suppose we have an earth and we have a moon. So of course the earth will have some mass, and the mass of the earth we know is 6 into 10 to the power to 24 kilograms. And similarly the mass of the moon, so if we have the value of the mass of the moon, so we can put it in the formula m1 and m2. m1 is for the mass of the earth and m2 is for the mass of the moon. And similarly we know that the distance between the center of these two objects, or the distance between the center of these two planets or the moon or two objects, is r. So we can put the value of r in this formula and we can take the square of the distance between them, and we can find the value of force, that what is the force existing between two objects. So in the case of the earth and the moon, the force is calculated to be 2 into 10 to the power to 20 newton. So 2 into 10 to the power to 20 newton of the force is acting between the earth and the moon. And similarly if we have two protons, and if we know the mass of the proton, okay, and the mass of the proton is 1.67 into 10 is power to minus 27, so we can use the equation to calculate the force between them, g m1 m2 over r square. Here the g is the gravitational constant, 6.67 into 10 is power to minus 11. m1 is the mass of the proton. This is the first proton having the mass m1. And m2 is the mass of the second proton in this case. So the distance between the center of these two protons is 1.5 into 10 to the power to minus 15. So we can put the distance here in this formula and we can calculate the force. And here the force calculated is 8.3 into 10 to the power to minus 35 Newton. So as you can see from the answer that the answer is 10 raised power to minus 35. So this is exactly very small value. That is why we say that whenever there are two masses and the masses are very small, such as the masses of the objects which we see on the earth, or any type of the masses which are having smaller masses, um, they will have a smaller gravitational force between them. And sometimes we say that we can neglect that gravitational force between them because we can't even feel them in our real life. For example, if on your table there are two books sitting side by side, then there's a force of gravitation between these two books, but you cannot feel that force of gravitation between them, and those two books are not even getting attracted towards each other. But can we say that there is no force between them? No, there is a gravitational force between those two books, but because the mass of those two books is so small that we can neglect that force. So the force is so small that it is negligible. So similarly, when we are calculating the force for bigger things such as the planets or the stars, so we know that the mass of the planets and the star is very big, and because the mass is very big, so that is why the force will be very big, and we can feel the force of gravity of the earth or of the Jupiter, of or some other star, but we cannot feel the force of the objects which we see around the earth in the daily life, because that force is negligible because of their smaller masses. Similarly, we can use the same formula to calculate the value of G. So as we know that F is given by G m1 m2 over r square, so we can use the same formula to calculate the value of G. So G can be given by F into r square divided by m1 into m2. So we can use this formula, and if we know the force, if we know the radius, that is basically the distance between two objects, if we know the masses of two objects, so we can also calculate the value of G, that is 6.7 into 10 raised power 2 minus 11 meter cube kilo per kilogram per second square. So what we have learned today, the summary of today's lesson. The gravitational field is the region of a space where the mass experiences a force. So of course, if there's a mass which is uh, placed into some region of or close to another mass, so that mass is going to create a gravitational field around it. And that gravitational field is an area where the mass or a second mass can experience a force. The gravitational field strength at a point is defined as force per unit mass acting on a small mass placed at that point. So we have discussed that if there is a earth and we are placing some object near to the surface of the earth, so there must be a gravitational field strength acting on this object, and that gravitational field strength will be given by the formula force per unit mass, that how much amount of the force is acting per unit mass of the object, that is given by G, and that is basically the gravitational field strength measured in Newton per kilogram. Gravitational field line is the direction of the gravitational force acting on a point mass. So gravitational field line are always represented by the line with the arrow, and the arrow is indicating the direction of the gravitational field. For a point outside a sphere whose mass is uniformly distributed, the sphere behaves as a point mass with its mass concentrated at the center. So if we have a sphere of a uniform mass, we can assume that all of the mass of the sphere is acting at the center. So we can consider it as a point mass. So this is basically a point mass representing the mass of this whole sphere. So instead of taking the mass or dealing with the whole sphere, we can consider it a point mass, and by considering it a point mass, we can solve the questions, so it makes the work easy for us. The Newton law of gravitational state that two point masses attract each other with a force that is proportional to the product of their masses and inversely proportional to the square of the separation. So as we have discussed before, that let us suppose we have two masses, or let us suppose we have 2 point masses. The point masses here are representing the point masses here are representing the mass of some sphere or the mass of some object. So we should know the mass of each of these point masses, and we should know the distance between these 2 point masses, that is represented by r, and we should know the value of G, that is 6.67 into 10 raised power 2 minus 11. So we can use the formula F equals to G m1 m2 over r squared to find the force present between these 2 point masses. And we know that this force will be directly proportional to the product of their masses, whereas it will be inversely proportional to the square of the distance between them. So that's all from the today's lesson. Thank you very much.